Welcome to the deep dive. Today we're getting into something really fundamental, something core to how almost everything mechanical works: torque. If you've ever heard an engine really rev up, or felt a smooth gear shift, or even just seen a big wind turbine spinning, well, that's torque right there. It's basically rotational force. We sometimes call it the twist. It's the force behind anything that spins, really. Car wheels, helicopter blades, you name it.
And capturing that twist accurately, well, that's absolutely crucial for engineers. I mean, think about it. Everything from a tiny drone motor to huge industrial gearboxes, understanding that torsional force, that's fundamental for performance, for efficiency, definitely for safety, and that's where torque transducers come in. Or torque sensors, same thing. These are really quite sophisticated devices. They measure that twisting force, that torque, and then they convert it into an electrical signal we can actually read and use.
Right, so it's not just if it's twisting, but getting a really precise number on how much twist there is.
Exactly that. And what's really impressive is the level of engineering involved. We're talking precision machining, often proprietary sensor tech, really specialized stuff.
Yeah.
Micro-engineered components designed to pick up tiny variations in force with incredible accuracy, sometimes using unique material properties to do it. This isn't just about getting a number. It's about unlocking performance, pushing efficiency, making sure things don't break under load. It really enables next level engineering.
Okay, let's unpack this a bit then. When we talk about these transducers, these sensors, what's the first big distinction? The main fork in the road for an engineer choosing one.
That's a great starting point because, your application really dictates the first choice. Broadly, there are two main types. First up, you've got reaction torque transducers.
Reaction torque.
Yeah, these are designed to measure static torque. So think force, but without actual rotation happening.
So nothing's actually spinning, like measuring the force needed to keep something from turning.
Exactly. Or maybe the force needed to tighten a bolt before it yields.
Yeah.
You see them a lot in process control, materials testing labs, assembly systems where you need to apply a known static twist.
Okay, that makes sense. So what's the other side of the coin for things that are spinning?
Right, for the dynamic stuff. Those are rotary torque transducers. As the name suggests, these actually rotate with the shaft. They're measuring the torque in real time while the system is in motion, while it's spinning.
Okay, so they're part of the rotating assembly itself.
Precisely. And a really big advantage here, especially for rotary ones, is how they often transmit the data. Many can do it wirelessly. No need for a physical cable connected to the spinning sensor itself, which, as you can imagine, can be tricky.
Oh, wow. Yeah, I can see how that would simplify things.
It's more than just simple, though. What's really fascinating is that this wireless capability, it actually enables measurements in situations that would be almost impossible otherwise. Think about testing a car's powertrain on a dyno, or monitoring the output of a huge gas turbine spinning at incredible speeds.
You just couldn't have wires flailing around in there.
Exactly. So rotary transducers, especially the wireless ones, are absolutely key for that kind of high-speed, real-world testing and monitoring.
That wireless bit really is a game changer then, not just convenient. Okay, so you figured out if you need reaction or rotary. But how does the force actually get into the sensor? How does it connect? I hear there are different styles.
Yeah, the physical connection is the next piece. So first you have what are called shaft-style transducers. These tend to be, longer, more like a section of shaft themselves. And they generally come in two flavors. You've got smooth shafts. The big plus here, really easy alignment. Getting things lined up is straightforward, and taking them apart is simpler too. And critically, no backlash.
No backlash is a big deal for precise measurements.
Definitely. Then you have keyed shafts. These often use a standard keyway, like you see on many motor shafts. They're usually simpler, maybe a bit less expensive, but you do need to watch out for potential wear over time. If that keyway starts to get sloppy, you can introduce backlash. And backlash means that little bit of play, that looseness.
Right. It can lead to measurement errors, maybe even vibration, especially under changing loads. So something to consider.
Okay, so shaft styles, smooth or keyed. What's the alternative?
The other main type is flange style. These look quite different. They're generally shorter, more compact, almost like a thick disc or a donut shape.
And they usually mount differently too, right? Bolting on the faces.
Exactly.
They have these pilot surfaces usually machined right onto the flange face, which really helps with centering the sensor accurately when you bolt it up. And, maybe more importantly, flange styles are typically much better at handling what engineers call overhung moments.
Overhung moments? Like side forces trying to bend the sensor?
Precisely. Forces that aren't pure torque, but are trying to pull or push the sensor off its axis. Think about a situation where the load isn't perfectly aligned, or maybe in a compact robotic arm. Flange styles tend to be inherently more rigid against those kinds of bending forces.
So if you've got a tight space or expect some of those side loads, flange might be the way to go.
Often, yes. It raises that important question for the design. What kind of mounting stability is really the priority for your specific setup? Is it pure torque transmission or resisting those off-axis forces?
That's a really good point. It's not just about measuring torque, but surviving the whole environment. Okay, so we've got type, we've got style. What else is critical for getting good, safe measurements? You mentioned couplings earlier.
Ah, yes. Couplings. Absolutely vital. Can't stress this enough.
Their job is basically to connect the machine's shaft to the transducer shaft, right?
Yes, but it's more than just connecting. A good coupling is designed to transmit the torque accurately, while also isolating the sensor from other forces. Things like misalignment between the drive shaft and the sensor, or axial forces, or even some vibration. The coupling needs to accommodate that without putting unwanted stress on the transducer.
So choosing the wrong coupling, or maybe installing it badly, that can mess everything up.
Oh, absolutely. It's a huge risk. Yeah, I mean, if you ignore proper coupling, you can easily introduce side loads or bending moments directly onto the sensor. Best case, your readings are inaccurate. Worst case, you actually damage the transducer. And these are sensitive, often expensive instruments.
Especially at high speeds, I imagine.
Critically important at high speeds. Any imbalance or misalignment gets magnified. The quality of the coupling becomes absolutely paramount then. You need something that transmits torque smoothly without introducing any extra noise or forces that could corrupt that clean torque signal. It's fundamental for both data integrity and protecting the equipment.
Okay, couplings are critical. Got it. What about how the sensor body itself is held? The mounting?
Right, a mounting strategy. Two main ways to go here, floating or fixed.
Floating sounds like it's not bolted down.
Pretty much. In a floating mount, the sensor body isn't rigidly attached to the base or frame. It's supported by the couplings on either side, the drive side and the load side. There's usually a flexible strap or a reaction arm attached to the sensor housing, but that's just to prevent the whole sensor body from spinning freely. It doesn't provide rigid support.
And when would you use that?
This is really suitable only for low-speed applications. Think static or very slow rotation. It's simpler, but offers very little stability.
So for anything faster?
For anything with significant speed, you absolutely need a fixed mount.
Meaning the sensor housing itself is bolted securely to a rigid support structure, like a heavy base plate or machine frame.
Exactly. This provides the stability that's crucial at higher speeds. It prevents vibration, helps maintain alignment, and stops the sensor from moving around in potentially unsafe ways. It really highlights how these design choices, the coupling and the mounting, are just essential for getting both accurate measurements and ensuring the whole setup is safe to operate, especially when things are spinning fast. You really can't cut corners there.
It all connects, doesn't it? Okay, so wrapping this up. It seems whether you're looking at static reaction torque or dynamic rotary torque, or choosing between a shaft style or a flange style connection, or figuring out if you need a floating mount for low speed or a fixed mount for high speed, every single piece matters. The couplings, the mounting, the sensor type itself, it all has to work together.
Absolutely. Every decision impacts the final result. It's all about getting those accurate, safe, and reliable measurements. That's the goal. That's what good engineering relies on.
It really is.
Yeah.
So think about this. Next time you see something spinning with real precision, could be the tiny motor making your phone vibrate, the complex gearbox in a car, or even a massive power plant turbine. Just consider that invisible dance of forces, that twist, and the incredibly sophisticated sensors working away behind the scenes, measuring, controlling, making sure it all performs exactly right. It kind of makes you appreciate the engineering that keeps our world spinning, doesn't it? Thanks so much for joining us for this deep dive.